This segment we're going to talk about the Brayton Refrigeration Cycle, also known as the reverse Brayton cycle. This is a gas refrigeration cycle. Air is most commonly used as a refrigerant. From state 1 to state 2, you go through an isentropic compression. This requires some amount of work. Then you go through an ideally constant pressure heat rejection process to your high temperature reservoir. Then from 3 to 4, you have an ideally isentropic expansion process within the turbine. That's where you get a work output. So it's the only type of refrigeration cycle where you do have a work output that we'll talk about in this class. And then from 4 to 1, you've got a constant pressure heat addition process from that refrigerated state. And that also occurs at constant pressure. If you look at the COP formula, so it's what you're interested in, QN, over what you have to put in, work net in. Work net in is equal to work in minus work out. And typically, with a vapor compression refrigeration cycle, for example, you didn't have a work out. Here you do, so don't forget about that guy. Let's look at this QN. If I look at the reverse Brayton cycle or the Brayton refrigeration cycle on a TS diagram, if I am modeling this as an ideal cycle, so there's no irreversibilities within our cycle, then the area between the heat addition process, it takes place from 4 to 1. And so if this is an ideal cycle, then the area underneath that curve from 4 to 1 represents the amount of heat that you add to the cycle. That represents your QN. Now, if you remember the vapor compression refrigeration cycle, that QN, that heat addition process, took place. It was a constant pressure heat addition process, and it took place in your evaporator. And so it went, the state of your refrigerant went from a two-phase substance to a saturated vapor. So we had a constant pressure phase change, and so it took place at constant temperature as well. Now, if that were the case here, if we were able to add heat at constant temperature, then you can see that the area underneath that particular curve would be a lot bigger. But as it is, we have a relatively low amount of heat that we're removing from that refrigerated space. And so compared to the vapor compression refrigeration cycle, your COP tends to be a little bit lower. So why do you use these? Well, they do have some specialized applications. Number 1, you can incorporate regeneration and you could obtain very, very low temperatures, and that's useful for cryopreservation, for liquefying natural gas, which requires very, very low temperatures. So if you look on a TS diagram, what we're looking at here is the simple Brayton refrigeration cycle. I've sort of like moved the diagram around a little bit. I brought that heat exchanger that used to be at the bottom, I've just kind of moved it up to the top. And you'll notice if you're paying attention to the numbering, I've left out number 3, and there's a reason for that, and you'll see why in just a second. But other than that, nothing has changed. This is a simple Brayton refrigeration cycle. So what I could do is I could add a regenerator in between here. So this allows me to move heat around in my cycle. And if you look at the TS diagram, between 5 and 1, you can see that the temperature there is lower than the temperature between 2 and 4. Now, heat is always going to flow from the hotter stream to the colder stream. And so you can see that heat is going to flow. It's going to be removed between 2 and 4 and then fed in between 5 and 1. And so what's going to happen, let's go back a little bit. What's going to happen is that's going to cool the air at the temperature. It's going to cool the air before it goes into the turbine. So at state 4, the temperature at state 4 is going to go down. And so obviously, as a result, the temperature at state 5 is also going to go down. So we've decreased the temperature before it goes into that refrigerated space, and that is how we're going to obtain those really low temperatures that you might need for those specialized applications. So now let's look at a TS diagram that incorporates the regeneration. So you can see that the temperature at 4 and 5 have gone down. And so you can obtain very, very low temperatures. The other place that this might be used is in aviation. So this is a gas propulsion. This is a gas turbine engine that's used for propulsion purposes. Air is flowing through this engine from the left to the right. So you've got air coming in, it passes through several components. You've got a diffuser, you've got a compressor, and you got some other stuff. Let's just stop at that compressor there. So we're compressing air already. And in the Brayton refrigeration cycle, well, that starts off with the compression of air. So you've got this ideally isentropic compression of air within the gas turbine engine as well. And so what you do is you bleed off a small amount of that air and you feed it into a Brayton refrigeration cycle. So so you bleed off some of that air, you reject some heat to the high temperature, the ambient, then you go through an ideally isentropic expansion within the turbine, you generate some amount of power that might be used for other purposes, and then that cooled air is mixed with the recirculated air and fed back into the cabin. So, all right, well, I hope that was helpful. Thank you for watching.